Welcome back to Module 2. So far in this course, we have explored the rigid, three-dimensional geometry of the Perovskite lattice and the mathematical tolerance factors required to keep it stable. Today we transition from structure to active chemical engineering. If you look at the screen, you will see a visual representation of the entire historical struggle of photovoltaics. On the left is a silicon wafer. It is gray, it is rigid, and it is the same everywhere in the world. On the right are vials of metal halide perovskite solutions, glowing in red, orange, yellow, and nearly transparent. How can the exact same underlying crystal structure produce so many radically different optical properties? The answer lies in a process known as compositional engineering. Today, we are going to learn how to break the rigidity of traditional semiconductors. We are going to treat our solar cell not as a fixed rock, but as a chemical sandbox, allowing us to continuously tune the bandgap across the entire visible light spectrum. To understand why this tunability is so revolutionary, we must first understand the fundamental limitation of traditional solar cells. In Module 1, we learned about the Shockley-Queisser limit. We proved thermodynamically that to achieve the absolute maximum theoretical efficiency under standard sunlight, a solar cell must possess a bandgap of approximately 1.34 electron volts. This presents a massive historical problem. The dominant technology in the world today is crystalline silicon. Silicon is a pure element. As you can see on the left, its atomic structure is entirely fixed by nature via rigid, highly directional covalent bonds. Consequently, its bandgap is fixed at roughly 1.12 electron volts. It is physically impossible to change the bandgap of pure silicon. You cannot tune it to hit that 1.34 optimal peak, nor can you tune it for specialized applications like transparent solar windows or indoor light harvesting. You are stuck with what nature gave you. Now look at the right side of the slide, the perovskite solution. Metal halide perovskites completely shatter this limitation. Because the ABX3 lattice relies on flexible ionic and hydrogen interactions rather than rigid covalent bonds, perovskites act as solid solutions. This means we can continuously mix and match different elements directly into the crystal lattice in varying ratios without destroying the underlying three-dimensional cubic structure. Let's look at exactly how this chemical tuning works at the orbital level. To change the bandgap, we have to look at the quantum mechanics of the energy bands themselves. In a standard lead halide perovskite, the conduction band minimum, the upper ledge where the free electrons sit, is formed primarily by the empty 6p orbitals of the central lead atom. However, the valence band maximum, the lower ledge where the holes sit, is much more complex. It is formed by a hybridized, anti-bonding overlap between the 6 orbital of the lead atom and the p orbitals of the surrounding halogen atoms on the x site. This is the most important takeaway of this slide. Because the halogen directly contributes its electron density to the valence band, the specific halogen we choose directly dictates the energy level of that band. By manipulating the halogen, we can pull the valence band up or down, radically shrinking or widening the bandgap. Let's put this into practice by tuning the X site. Let's look at the left side of the diagram. Pure methylammonium lead iodide. Iodine is a very large atom with weakly bound outer electrons in its 5p orbital. This creates a relatively shallow valence band, resulting in a narrow bandgap of roughly 1.55 electron volts. This material absorbs almost the entire visible spectrum, which is why it appears pitch black to the human eye. Now let's completely remove the iodine and replace it with bromine. Bromine is a smaller, much more electronegative atom using its 4p orbitals. The covalent interaction with the lead becomes stronger, which physically pulls the valence band deeper down in energy. Because the valence band drops, the gap gets larger. The bandgap widens to 2.30 electron volts. This material appears bright orange, as it can no longer absorb red light. If we go even smaller and substitute chlorine, utilizing its 3p orbitals, the valence band is pulled incredibly deep. The bandgap widens massively to 3.10 electron volts. This material is completely transparent, absorbing only invisible deep ultraviolet light. Smaller, more electronegative halogens push the valence band deeper, widening the gap. But here is where solid-state chemistry feels like magic. We are not forced to choose between pure iodine, pure bromine, or pure chlorine. Because all three of these halogens share the exact same -1 oxidation state, they can be homogeneously alloyed together in any ratio we desire. We can take a crystal lattice and fill 80% of the X sites with iodine and 20% with bromine. The benefit of this homogeneous alloying is continuous tunability. We are no longer restricted to a few discrete bandgaps. As you can see on the color spectrum at the bottom of the slide, by carefully dialing in the exact ratio of iodine to bromine, we can dial in the absorption edge of the solar cell to literally any wavelength across the entire visible spectrum. We can custom build a solar cell for any lighting environment on Earth. If we mix two halogens together, how do we know what the new bandgap will be? If the bandgap shifted perfectly linearly relative to our mixing ratio, it would obey what is known as Vagard's law. You would simply draw a straight, dashed line between the pure iodine bandgap and the pure bromine bandgap, and calculate the weighted average. However, look at the red curve on the graph. In reality, because bromine and iodine are different physical sizes, mixing them creates internal strain on the crystal lattice. This atomic size mismatch causes the orbital overlap to deviate slightly from a perfect linear transition, resulting in a bowing effect. The bandgap sags slightly below the linear prediction. In solid-state physics, we correct this using a mathematical term called the Bowing parameter, denoted by the lowercase letter b. The equation states that the new bandgap, E sub g of x, equals the linear weighted average of the two pure materials, minus the Bowing parameter multiplied by the fraction x, multiplied by 1 minus x. Let's run this calculation for a highly specific, real-world application. Assume we want to engineer a material with 20% bromine and 80% iodine, so our fraction x is 0.2. Our parameters are set. The pure iodine bandgap is 1.55 electron volts. Pure bromine is 2.30 eV. And empirical testing tells us the Bowing parameter B for this specific alloy is 0.30 eV. Step 1 is the linear prediction. We take 80% of 1.55 and add it to 20% of 2.30. This gives us a baseline prediction of 1.70 electron volts. Step 2 is the Bowing correction. We subtract our Bowing parameter, 0.30, multiplied by our fractions, 0.2 times 0.8. This yields a tiny subtraction of roughly 0.048 electron volts. Applying this correction, our final precisely tuned bandgap is exactly 1.65 electron volts. Why are we so obsessed with hitting exactly 1.65 electron volts? Because it is the ultimate killer app for perovskites. A 1.65 electron volts bandgap is the absolute perfect optical filter to act as the cell in a cell attraction in a perovskite silicon tandem solar cell. It absorbs the high-energy blue light at a massive voltage, while perfectly passing the low-energy red light down to the silicon panel beneath it. This specific composition is what is driving tandem efficiencies past 33% today. Before we wrap up, we must address the final tuning knob, the A-site cation. Unlike the halogens on the X-site, the organic A-site molecule does not directly contribute any electron orbitals to the conduction or valence bands. However, changing the A-site still tunes the bandgap indirectly through a physical mechanism known as steric hindrance. Look at the graphic on the slide. If we swap the standard methylammonium molecule for a slightly larger organic molecule called formamidinium, or Fa, the larger molecule acts like a balloon inflating inside the void. It physically pushes the surrounding lead iodine octahedra outward. This expands the entire crystal lattice. As the lattice expands, the critical lead and iodine atoms are pushed further apart, which weakens their orbital overlap. This weakened overlap actually narrows the bandgap. By switching from methylammonium to formamidinium, the bandgap of a pure iodine perovskite drops from 1.55 electron volts down to roughly 1.48 electron volts. This tiny physical expansion pushes the material incredibly close to the ideal Shockley-Queisser theoretical peak. To summarize today's lecture, unlike traditional rigid semiconductors like silicon, perovskites act as solid solutions, allowing for continuous chemical mixing. Our primary method for tuning the bandgap across a massive range, from 1.5 to 3.1 electron volts, is X-site engineering, swapping iodine for bromine or chlorine. We can then use A-site engineering to perform subtle structural tuning via steric hindrance. And finally, the ultimate goal of all this compositional engineering is the killer app of photovoltaics, creating the perfect wide bandgap top cell for perovskite silicon tandems. Now that we know how to tune the colors and the energies of the crystal, we are ready to look at how electricity actually moves through it. In our next lecture, Lecture 2.4, we will dive into the incredible optoelectronic properties of perovskites, exploring excitant binding energies, ambipolar transport, and record-breaking diffusion lengths. Thank you for your attention, and I will see you in the next lecture.